So the last thing we're going to talk about in fluid physics is Bernoulli's principle. And Bernoulli's principle is really relating the idea of conservation of energy to the movement of liquids. So when the velocity of a liquid in a tube changes, the pressure also changes. So if we have this scenario, just like we saw on the volume rate of flow video, where we are decreasing the area, the cross-sectional area of the pipe, we know, or we've shown, that the velocity of the fluid moving through must be increasing. And it's sort of counterintuitive what happens to the pressure. As you hold your thumb over the end of a hose, you are increasing the velocity of the fluid. And a lot of people think the pressure is increasing because they feel the water sort of striking their thumb, right? And they think that that means that there's more pressure. But really, Bernoulli's principle shows and proves through the conservation of energy that as the speed of the fluid increases, the pressure within the fluid decreases. And I'll show you why that's true. So let's go back and think about the idea of conservation of energy. So energy is always conserved. It can only change forms, right? So if we're to increase the velocity of the fluid, that's going to make the kinetic energy of the fluid increase or go up. Right? So in order to keep our value of energy constant, that means some energy value must be decreasing as the scenario is changing. If we look here at this example of this pipe where we know that the height really above the some relatively low position, we're going straight across here, we would draw some line through straight through the fluids as the point of where the height of the fluid is, stays constant. So potential energy, or essentially gravitational potential energy, must be exactly the same. So in order for kinetic energy, or for the energy to be conserved, kinetic energy increases, potential energy is constant, there must be some work done by the fluid that is causing energy to leave the substance. So what kind of work is that? If we go back and we look at our equation for work that we learned several units ago or in the last course, work is equal to force times distance. And we learned that pressure relates to force in that it's the force per unit area. So if I solve this equation for force and sub it into my work equation, which we will apply as we move into talking about thermodynamics as well, we get that work is equal to pressure times area times the distance, right? So I've just subbed in pressure times area for force here. And then if I see, well, cross-sectional area times distance actually gives me volume of this fluid. So it ends up being pressure times volume. And we know that the volume of the fluid as it moves through is going to be constant because of volume rate of flow. So that shows that pressure is decreasing in order to conserve energy. So if we look at Bernoulli's equation, we see that there's some situation at the beginning where there's all sorts of types of energies, and that has to be equivalent to the energies at the end. And if you notice here, it says it's not just energy, but it's energy per unit volume. So again, we're dealing with this idea of where H is the same in both locations. We'll look at an example here in a second where it's different. And we would have over here the pressure. We would have also the kinetic energy per unit volume. So we know kinetic energy is 1/2 mv squared. So if it's per unit volume, then we would have m over v, which is rho. So we can plug that in there. So 1/2 rho v squared, plus the potential energy, and it's essentially gravitational potential energy per unit volume. So it is, m over v gh, which gives us rho gh. Now this looks a lot like gauge pressure, but this h is different. This is the height above some relatively low position, which is what gravitational potential energy is. And again, we'll look at that in a second. Right now, for this example that we're using, h is the same on both sides. So really this term and this term are negligible. And we're just looking at the pressure and the kinetic energy per unit volume. So as we decrease the radius of the tube, we know from volume rate of flow that that's also going to cause the velocity to go up. So over here we have a small velocity in this section, and then over here where we narrow the tube, we're going to have a large velocity. So the kinetic energy per unit volume is increasing. So in order to keep this expression true, that means that the pressure over here on the left must be greater than it is over here. So pressure where the fluid is moving faster must decrease. All right, so let's look at an example where height really does matter. So let's say we have a refinery and there's ethanol flowing through a pipe and it has some specific velocity and pressure at this location. And then at the very bottom, we need a different sort of pressure and we're given we said that the velocity doesn't change, and we're given a density. So let's go ahead and try and figure out what the height of the pipe would be. And I'm going to pull up the ML here. So again, this is an example where we're sort of eliminating one of the variables, right? So because the velocity is constant from here to here, then that's going to cause my velocity to sort of even out on both sides, or my kinetic energy per unit volume to even out on both sides. And quite often they would like to they give you equations where you would have to use volume rate of flow between here and here, so using AV equals AV, so you can get the velocity and the change in kinetic energy. But for this case, we'll just keep it a little bit simpler so we can just look at how the height affects and what that height actually is, right? So up at the top, it says here where pressure is 1, I have 101,300 pascals. So 1.013 times 10 to the, that's fifth pascals. And it says, even though you can't see it, it gives me the density is 789. You can see that. And it gives you the velocity as being 1 meter per second. Right? And then at the second position here, I have the pressure, and it's covered up, but it says that it wants it to be 2 atmospheres. It has to be 2 atmospheres down there at the bottom. So it's that's 2.026 times 10 to the 5th pascals, which is this number right here. And then again, same density of 789, and then the velocity we said stays the same. All right, so our equation is, we're really trying to find the difference in the height, what the change in the height would have to be. So over here, I've got pressure 1 plus rho GH plus 1/2 rho V squared is equal to P2 plus rho GH plus 1/2 rho V squared. So if I just plug in all of my numbers, I'm really trying to find what would be the change in H. So what I'm going to do is I'm going to set one of my H's equal to 0. So it gives you this reference point right here of this being the ground, but I'm going to make my lowest relative position here be 0. Right? So this is where it gets a little confusing in terms of gauge pressure. You would think that right here, or over on this side where we're dealing with the second thing, that would be gauge pressure, which would be the height of the liquid above it. But that is not the case, right? So what it is the gravitational potential energy that the fluid has up here wanting to flow down. So right here on this side, this term would actually be 0 if I make this height right here 0. So that will cancel. And I'm really trying to solve for this H then. So I would get 100, or I'd have 1.013 times 10 to the 5th plus 789 times 10 times H, which is my variable, plus 1/2 the density, 1 squared is equal to, it ends up being a big mess, 2.026 times 10 to the 5th, that term cancels, plus 1/2 789 1 squared. So you can see over here, if I were to do this and then subtract it from both sides, this term actually would cancel as well. And so I'm going to get that 7,890H is equal to this minus this, which is 1.013 times 10 to the 5th, because I've just doubled my pressure. So if I just take that and divide by this, it should give me the height of the pipe. So let's do that really quick. 1.013 divided by All right, so the pipe would have to be about, I know it's kind of hard to see, it's tiny, but the pipe would have to be 12.84-ish meters above. All right, so that's Bernoulli's principle.